My name is Trevor Brooks. This is my sophomore year at Embry-Riddle, and my second year on the team. I am team lead, also air boss on the flight line, and in development I worked a lot on mechanical and a little bit on the mission processing side.
I'm Reed Levick. I'm a freshman at Embry-Riddle Aeronautical University. This is my first year on the team with no previous UAS experience. I'm part of the mechanical development of Beluga and also autopilot operator for the flight line.
My name is Matthew Helms. This is my freshman year at Embry-Riddle. It's my first year on the team. On the flight line, I'm the safety pilot, and I've been flying RC planes for 6 years. And the development, I work on the mechanical side.
Hi, I'm Jamie Barnes. I'm a freshman at Embry-Riddle. This is my first year on the team. In the development side of Beluga, I was in charge of the organization of the team, the testing, and the communications. And then on the flight line, I am support crew.
I'm Alan Jackson. I'm a freshman at Embry-Riddle. This is my first year on the team. I'm a payload operator on the flight line, and I do software development.
I'm Sean McDonald. I'm a sophomore at Embry-Riddle. This is my second year on the team. On the flight line, I'm a payload operator, and in-house, I'm the lead software developer.
This is our platform for the 2017 SUAS competition. We are using a Skywalker X8 flying wing. For takeoff, we are using an electric winch-style launcher. For imagery, we are using a Point Grey Chameleon 3 5-megapixel camera with a 2-axis brushless gimbal.
Our platform this year is powered by an Aptus Aerospace Grid 6 6-cell lithium-ion battery. The propulsion system for our platform is a Tiger Motor MN5208 brushless pancake motor driven by a 40-amp T-motor ESC. The system is efficient and increases our flight endurance.
Our payload system consists of an NVIDIA Jetson TX1 running OpenCV for image processing that is connected to a custom version of Q ground control that has been modified for the interrupt task.
This year at competition, we are confident in our ability to accomplish the autonomous flight, detection, localization, and classification, actionable intelligence, and waypoint capture tasks. We will be attempting the stationary obstacle avoidance and emergent target tasks. However, we will not be attempting the moving obstacle avoidance, air delivery, and off-axis target tasks. In order to find out which material has the highest strength to weight ratio to use for the skin of our airplane to increase its durability and longevity, we conducted many different tests on different foam finishes in order to find out which material was best suited for this application. We conducted 2 different types of foam finish testing on these different types of foam finishes. 1, a bending test, and 2, an impact test in order to most accurately replicate what they will experience on board the aircraft during flight and during landing. When selecting a foam finish used aboard the aircraft, 2 major considerations were kept in mind: rigidity and weight. Added rigidity would help protect the aircraft in the case of a hard or unplanned landing. As you can see, laminate drastically outperforms every other material in both the bending and compression tests. Because of this, laminate was used on the wings of the aircraft due to the high probability of the wings experiencing bending forces. Monocoat was used on the body of the aircraft due to its high probability of experiencing compression, and Monocoat's high compression rating as well as its low weight made it the perfect material to select. For our battery selection, we tested 3 different types of batteries at cruise in order to see what kind of flight time we could get out of each of them. First, we tested a 10,000 mAh 4-cell battery from Thunder Power, which gave us about a 75-minute flight time. Second, we tested a Grid 4 battery pack at 17,000 mAh 4-cell lithium-ion from Aptus Aerospace. That gave us about 120 minutes of flight time. Third, we tested a Grid 6 battery pack at 13,000 mAh 6-cell lithium-ion battery from Aptus Aerospace. That gave us about 180 minutes of flight time. We were able to achieve that flight time because the Grid 6 battery operates at a higher voltage, which allowed us to use the more efficient MN5208 motor from Tiger Motor. Because of the high efficiency and long duration flight we were able to achieve by using the Grid 6 battery in combination with the MN5208 motor, we decided to use those 2 on our platform for this year's competition.
After having decided upon the Grid 6 battery pack and the MN5208 Tiger motor, we tested a selection of props at cruise conditions and monitored the power draw. We selected a 15-inch diameter, 8-inch pitch folding propeller due to its lowest current draw.
In order to find an embedded system that best fit our needs, we did a lot of research, and through some recommendation among other companies and advisors, we found the Jetson TX1. Then we ran some open graphics library tests between the Jetson TX1, Odroid XU4, and Raspberry Pi 3, and the Jetson outscored all of them. Jetson TX1 is capable of 1 trillion floating point operations per second, or 1 teraflops. This allows us to do real-time image processing on the plane.
We are confident in our platform's ability to perform autonomous flight because we've used this airframe and autopilot system for the past 2 competition seasons. This platform specifically has logged more than 12 hours of autonomous flight over the course of 40 flights. We have also logged more than 70 flights on an identical airframe.
In order to optimize the camera settings for object detection on board our platform at 100 meters altitude, we used Point Gray's FlyCap software to adjust settings like exposure, ISO, gain, and shutter speed. For a preliminary test, we set up the camera 100 meters from a tree line and used the FlyCap software to make iterative adjustments to find the ideal settings.
In an effort to ensure that our auto detection, classification, and localization algorithms on board our platform are competition ready, we've developed a set of reconfigurable targets. These targets allow us to change the individual characteristics of each target for every flight test to ensure that our algorithms are unbiased and robust.
One of our more significant changes this year was in our communication system. Opposed to previous years where we used multiple different connections for our communications, this year we're using one 2.4 gigahertz connection for all of our communications. In the plane we have an omnidirectional antenna, and on the ground we have more directional antennas. These utilize a Ubiquiti rocket and bullet to improve signal strength. Our autopilot telemetry is routed through our onboard computer, allowing us to utilize the same communication system as the rest of our plane.
Before every flight test, a checklist is completed to ensure that all the components necessary for the flight test are present. These checklists are completed on paper and on Google Forms for easy archiving. Not every test is a full mission demo, as each test has a specific goal in mind, like waypoint navigation or camera tuning. A specific test is planned for each flight. Thus far, multiple individual component tests and mock missions have been completed. However, more mock missions will need to be completed before competition in order to ensure the smooth integration of all of our systems.